Hey everybody, here's tutorial 3 part 3 where we're going to review jit.gen. So first I'm going to take tutorial 3 part 2 and just hack out parts that we're not going to be working with today. So I'm going to take out the entire planet structure. I'm going to leave my pattern storage in auto pattern, but I'm going to change the name of my pattern storage so that it will have a name different from part 2, so that when I save the file, it'll automatically load the file name part 3 instead of the previous name. And I'm going to remove things to make space here. And I'm going to de-encapsulate, that's Command-Shift-D. So I can see a bit more easily what I'm doing. I'll even de-encapsulate that. The purpose of encapsulation is to make the screen less cluttered and to make things easier for you. You only want to encapsulate once you have everything working the way you want it to. Because once you encapsulate something, you're in essence hiding it and making it harder to see what's going on. So while you have space on the screen, don't encapsulate. In fact, de-encapsulate and leave things exposed like this so you can really see what's happening. So I'm going to just start with a blank jit.gen. And this is, of course, still holding on to the building shapes from before. So I'm just going to retype mypoly 50. And that's going to reinstantiate all 50 of those objects into our familiar red balls that we start with. Now you see how the balls are kind of quivering here. That's because they're squished into too small a world box. So let's make the world box a little bit bigger here. And now you see they have room to spread out and they're not bouncing against each other. And one of the things you've probably noticed is when you're working with a camera that's, for instance, like this camera 20 meters away, it's very hard to grab your handle. So you can add a larger radius to your jit.gl handle with the @radius, say 5 meters. And that gives you a pretty easy handle to work with there. I'm going to take away our dramatic lighting for now. So it's a little bit easier to see what's going on. And as we've seen throughout several tutorials, this is a handy way to turn on and off objects. Enable $1 connected to a toggle just allows me to quickly turn off the lighting. I can also remove our starry background here. That's not necessary. And you see the stars are still there because they've already been sent through. But if I recreate my world here, we'll see that when I turn it back on, there are no stars now. It's a gray background. So let's take a look back into jit.gen. So what we're doing right now is we're taking random values. We're taking 50 sets of 3 values and passing them into our jit.gen. So let's see what that does for us. And that sends all of our spheres right into the center of the world, and they'll crash up against each other. Why? Because they're too close together. So we want to spread them out in space. And jit.gen is a great tool for that because it allows us to do some simple math on every value in the matrix. So the jit.noise is creating a whole bunch of coordinates that are all very close together. They're all between 0 and 1 meter. So all the balls are going to bounce into each other, and we're just going to see a big collision. So inside the jit.gen, we can perform some math on the entire matrix, every incoming value. And we simply do that by using the times sign and saying, for instance, times 5. So instead of the values being between 0 and 1 meter, they're now between 0 and 5 meters. We're just multiplying every value coming in by 5. Whether it's x, y, or z, it's all getting multiplied by 5. So now, when I send the noise in, I see that my spheres are bumping into each other less. Why? because they're being sent to coordinates in a larger area. But notice they're all above and to the right of center. Let's turn off the floor for a second here. I'll just copy this enable structure, connect it to my floor, and turn the floor off. And just so we can see where center is, I'm going to create a new object that is in the center, and I'll give it some material. And notice you can use the same material for multiple objects. Make it a little bit smaller. So we could see that our random cluster of spheres is all in the upper right-hand quadrant. Why is that? Well, it's because jit.noise is giving us random values between 0 and 1, and we're multiplying those values by 5. So the output is random x between 0 and 5 meters. That's from center to 5 meters out. A random y of 0 to 5 meters. That's from 0 to 5 meters up. And a random z of 0 to 5 meters, which if I angle this and look at the top, we'll see is 0 to 5 meters towards the camera location. Reset this. And those are all positive values. Those are all greater than 0 values, which in our coordinate system all means up and to the right and towards the camera. So things are exactly where we would expect them to be. And even if I multiply it by a larger value, say by 10 meters, that's still spreading out my spheres in a positive direction. Positive x, positive y, positive z. So we see they're spread out further, but they're still all in the upper right quadrant. So how can we solve that problem? Well, in Gen, we learned about scaling, but we also learned about biasing. So the values coming in are now between 0 and 10 meters. So if we wanted them to be centered around our 0 point, the center of our world, we can just subtract 5 meters from all of this. This is going to take our 0 to 10 meter distribution and shift it on the x, y, and z axes 5 meters. So now instead of being 0 to 10 meters, it's -5 to 5 meters, and you'll be able to see immediately what this does. Now our random arrangement is centered around 0. But there's a problem with scaling and biasing in this way, because if I suddenly decide that I want it to be over 11 meters, it's going to be slightly to the right. I have to go back in here and subtract 5.5 meters to center it again. So what's much easier to do is bias around the center before you scale. So I say minus 0.5, and now I'm taking my incoming range of random numbers between 0 and 1, and I'm shifting them all by 0.5. So now my incoming range is minus 0.5 to 0.5, and whatever I multiply here, I never need to change my bias. But sometimes you don't want to scale everything equally. And in fact, sometimes you don't want to bias everything equally. And this is where the vec object comes in. So for instance, if I want to spread my objects out more widely than high, I can say vec 15, 5, and maybe 0. I don't want to spread my objects out at all on the z-axis. And then I need to remove the typed in argument in the multiply, because now I'm multiplying by a vector. I'm multiplying x and y and z by separate values. So I'm biasing everything around the center and then scaling my x across 15 meters, but I'm only scaling my y across 5 meters, and I'm not scaling my z at all. In fact, I'm zeroing out my z. So let's see what that does. And now we can see that my x is spread out wide, my y is spread out, and my z is not spread out at all. And now I'm going to encapsulate, because this is working the way I want it to, and I don't need to look at it anymore. So I'm going to Command-Shift-E, encapsulate, and just call this pos. And then I can copy that. That's Option, click, and drag is a quick way to copy. Another quick way to copy is Command-D for duplicate. Another quick way to copy is Command-C, then Command-V. And I'll make another one for color. I should de-encapsulate it because I haven't seen it work yet. And until I see it work, until I know it's working the way I want, I don't need to encapsulate it. So let's use these same random values and affect the color. Well, in color, instead of having X, Y, and Z, we have R, G, and B, red, green, and blue. The important difference is in position we have negative values. Negative means left of center on the X. But negative has no meaning in color. Neither does values that are greater than 1. So we can go into the jit.gen and we're going to have to think about it differently. We're not going to be biasing things around the center because that doesn't make sense with color. We're not going to be multiplying by big numbers like 50 and 5 or adding big numbers like 4 because that doesn't make sense with color either. So let's just to start out, not do anything in the jit.gen and see a bunch of random colors. And we can see already they're organized because we're using the same random values to colorize them and change their position. Let's do a very simple scaling, which is to multiply by a vector of 1, 0, 0. That means that the random red values will pass through, the random green and blue values will be multiplied by 0 or zeroed out. And now we get shades of red. Since we're using the same random values for position and color, our lowest values, our lowest random values, are going to place objects on the left and make them dark, close to black. Our highest values are going to place objects on the right and make them bright red. Now, if we don't want that, we just can use different random values. I'll use 2 different jit.noise, and now they're mixed together because we're using different random numbers to control position and color. But if we use the same random numbers to control position and color, then we see that our objects are organized. We could do the same thing with scale. So let's take this and encapsulate it again. Now I've got a P color, and I'll take this, duplicate it here, de-encapsulate this, and work with scale. Now, negative scale doesn't have a meaning, so I don't need that. I'm not going to be making big scales like 50 and 5 or adding 4, so I'll remove that. Let me just take these values and pass them in, and also let me change my objects to a different shape, like to cubes. So I'm going to target all of them. Target 0, shape, cube. And now they're all cubes. So now I can go into this jit.gen and just, again, I'll just let the random values pass through, values between 0 and 1. So I'm going to have cubes of all different sizes with the possibility of a cube that has no thickness or no depth, all the way up to a cube that's 1 by 1 by 1. They're kind of getting in each other's way, so the first thing I can do in here is just go and knock them all down in size, scale them all to half. Try it again, and now they're much less in each other's way. And if I want to do a proportional scaling, I can certainly do that as well. For instance, perhaps I want to have them have a random height, but a fixed width and a fixed depth. So now, scale them by a vector. The width, I want to remove the random values. The height, I'll scale by 0.5, and the depth, I want to remove the random values. Now I have objects of 0 width and 0 depth. So I need to bias after the fact and give them a fixed width. So I'll say give them a fixed width of 0.5 and a fixed depth of 0.5. So here, I'm taking the random values in. I'm multiplying the x values by 0. I'm multiplying the y by 0.5, meaning I want the randomness to have effect, but only in a range of 0 to 0.5. And the z values, I'm also zeroing out. And then I'm adding a fixed value to x and a fixed value to z. So now I'm getting cubes that are going to vary randomly in height, Since they've bounced off of each other, they're in a lot of rotation. I'm just going to rotate them all to 0, 0, 0 so that they straighten out. There we go. You can see much more clearly that you've got cubes that are all the same depth and they're all the same width, but they're different heights. So let's just look again at why we have that. We're taking the random values about width and multiplying them by 0, removing them, and then we're adding a fixed value of 0.5, which means that every cube is going to have a width of 0.5. We're taking the random values about height and multiplying them by 0.5 and adding 0, meaning we're going to have a range of heights from 0 to 0.5. And then we're taking the random information about depth, erasing it by multiplying it by 0, and then adding a fixed value of 0.5, which means all of our cubes are going to have a fixed depth of 0.5. And we can see, because we're using the same set of random numbers for all three, there's a relationship between the color, the position, and the scale, in that cubes that have low random value for y are going to be close to the bottom and thin, and their color is not going to be affected because we don't have any color happening on the y-axis. But we certainly could have these y values influence color. If we go into our jit.gen and zero out or turn off the influence of x on red, we can turn on the influence of y on green. So now we're going to get a range from black at the bottom to green at the top. And of course we can bias as well. So we can, for instance, add a fixed value to our red, add 0.5 to red. So our red is going to be fixed at 0.5 because we've already zeroed it here by multiplying it by 0. So the random values are not passing through. And then we're adding a fixed value of 0.5. And we see that we get red at the bottom passing through yellow in the middle, and we get a lighter green at the top. We don't get the bright green that we had before. Now, let's take a moment and think about why this is. Well, at the bottom, green is 0, but red is 0.5. So we're seeing the redness. As we approach the middle, green approaches 0.5, and red is fixed at 0.5, so we see the color that we get when red and green are the same value, which is yellow. As we go towards the top, y increases, so green increases, but red remains fixed at 0.5, so we get a green mixed with a little bit of red, or a yellowish green, so not the bright green we were seeing before. And so this is the way in which you can work with colors. And you might say to yourself, aha, I see a big limitation here, which is verticality. Y is always tied to green, horizontal is always tied to red, and depth tied to blue. And this is true because we haven't looked at a couple of things yet that would allow us to manipulate the dimensions and the colors independently. But we do have access to a very simple way to do that already. If I de-encapsulate here, we can now really see what the difference is between using prepend and using a message with $ arguments. Because $1 means I want my red value to be set by the first value in each cell of the matrix, which is also x. $2 means I want my green to be set by the second value, and $3 means I want my blue to be set by the third value. So, for instance, we can just change these around and have the blue influenced by the vertical. So now we see a totally different palette of colors here. Red at the bottom, purple at the top. And just to simplify this, we'll go back into the jit.gen, remove the bias, so our colors are a bit simpler, and we'll see that we get black to blue. Why? Because $2, our y value, is now influencing our blue channel instead of influencing our green channel. And we can also do, and we've seen something like this before, we could have our y channel influence all three colors, which means we're going to go from black on the bottom to white at the top. We can also, instead of adding fixed values in our jit.gen, we can scale in the jit.gen and then do any fixed values right in the message. So we can say, all right, we always want red to be 1, fixed value of 1, but we're going to have our y position determine green and blue. And there we go from red on the bottom, because y is 0, so we get no green and no blue, but we always get 1 of red. Red fading up to white at the top. So you see there's a tremendous amount of versatility here, even though we haven't looked at all of the features within the jit.gen. There is one important addition, though, particularly when working with color. When you're coloring objects, you really are limited to a range of 0 to 1. So you might be tempted, for instance, to multiply your y value by 2. You can't really do that because that's going to give you illegal values. That's going to give you values greater than 1. Similarly, you might be tempted to bias by a negative number. For instance, adding negative 0.5 from the red, and you can't do that because it's going to give you negative values for red. So there's a very handy object called clip, and clip just sets a minimum and a maximum value. So clip 0, 1 says any value that falls below 0 on any dimension, x, y, or z, red, green, or blue, any value that falls below 0 is going to be set to 0. All negative values will become 0. And any values that exceed 1 will become 1. So it clips off illegal values. So this is a very good object to just add in any color manipulation that you're doing, because it will allow you to work with multiplications, subtractions, additions that would create illegal values, and then this will make all of your color values legal passing out of the object. And so here I'm getting a very similar effect. But if I set this back to normal, I would be generating greens that are too bright, and I would be generating illegal red values. But because of my clip, I'm keeping everything within the 0 to 1 range. And there I can get a nice effect where I have a little bit of orange objects on the bottom, but the majority of my objects are shades of green. That's because I'm allowing the random red values in, but I'm subtracting 0.5 from them and then clipping them at 0. So you see there's a really wide range of creative possibilities here in terms of dealing with color once you start manipulating your $sign arguments and scaling and biasing within your jit.gen. Now, one thing that you may have noticed already is that, okay, we're able to create random arrangements, but we're not actually able to put things just in a line, which seems like a very straightforward thing to be able to do. What if I just want my blocks to line up from left to right, equally spaced? Well, that's because that requires a separate object and a separate concept that we haven't looked at yet. I'm going to go back in here and just change this back to our very simple red to black arrangement. Black on the left, red on the right. I'm going to re-encapsulate. And I'm going to knock down the number of objects we're working with. I'm going to knock us down to just 20 objects. So I change my jit.noise so it generates 20 triplets of random values, and also my poly, knock it down to 20 objects as well. And my shape reverts to a sphere because internally in my poly, my shape is set to sphere. So these objects are sort of spread out in an organized straight line, but not really. They're actually, it's the result of them all being created in the same spot and spacing out. So I'm randomizing my position, and because I'm using the same noise for position and color, I'm seeing an organization to the color. Objects that have a low X will also have a low red. I'm going to use two separate randomizers so that we don't see that correlation. And I'm not working with scale right now, so I'll leave it there, but I'll disconnect it for the moment. So if I want to arrange these objects on a line, what I need to do is I need to have a non-random distribution of values across one of the axes. So for instance, if I want all of these spheres to line up on the x-axis, I need to generate values that go smoothly from, say, -1 to 1 on the x-axis. And that is done with an object called SNORM, snorm. And that stands for signed normalized values. Notice that it does not have an inlet. There's no inlet to snorm because it is actually generating its signed normalized values based on the size of the matrix that's coming into the jit.gen. So if I just plug snorm directly into a multiply and multiply across 15 on the x-axis. And notice I'm not using my random values at all. I still have my in1 here, but there's no connection. I'm just using my signed normalized values and saying take those signed normalized values from -1 to 1 and multiply them by 15 meters to spread my objects out evenly on the x-axis. And now we finally see a spread out even arrangement on the x-axis. I'm going to get rid of my reference cube. So let's take a look at why that works. Signed normalized values is saying, all right, you've got a matrix with 20 cells in it. So take the 0th cell and put a -1 in it. Take the 19th cell and put a 1 in it, and fill in all the rest of the values evenly from -1 to 1. And then because it goes to -1, that's the S, that's the signed normalized values. And then multiply that times 15, so we get a range from -15 meters to 15 meters. And we can do the same on the y-axis if we want to create a vertical stack. Now we have vertical straight line arrangement of objects. And of course we can combine the randomness with the normalized values. So I can take my arrangement, I'll put it back on the x-axis, my smooth arrangement of positions on the x-axis, and combine it with randomness on the y-axis. So I'm taking my random values coming in 1, I'm zeroing out my x and my z, but I'm multiplying my y by 5 meters. I'm taking my signed normalized values and multiplying them by 15 on the x-axis, and then I'll take all of this and add it together. So I'm going to get an even distribution across x, but I'm going to get randomness on y. So let's add scale back into this picture. I'm going to change my shapes back to cubes, reconnect my scale, and I'll do the same thing here, except instead of using snorm, this time I'm going to use norm. Norm is the same as snorm, except it's not signed, meaning it doesn't go into the negative. So norm gives me an even distribution between 0 and 1. So I could take my norm values, disconnect my randomness entirely, and I'm just going to say I want the heights of my objects to go from 0 to 1 meter, and my width and my depth will be fixed at some value like 0.5. And we can see on the left, I have thin going all the way to thick on the right, and they're not random. So if I remove my vertical randomness here, actually I'll just delete this, right? So no random activity, simply signed normalized values determining x position and normalized values determining height. I get a totally organized arrangement of objects that get taller as they move to the right. But I still have randomness affecting color. And so even though I have a jit.noise here, I'm not actually using the random values from this jit.noise at all. Notice my in1 is not connected in terms of position, and it's not connected in terms of height. And in a case like that, you don't actually even need the jit.noise. You can simply use a jit.matrix. It'll give you the same result. But it's actually fine to use a jit.noise as long as you're aware that you're not actually making use of the random values that you're generating. And the same thing can be done in color. And in color, we would obviously use norm because we don't want signed values. We don't want negative values. So we can apply the normalized values to redness, and I get a smooth progression from black to red.